Hello everyone, I welcome you all to series of my video lectures on theory of groups. In this session, we will have a introduction to group theory. We will consider the definition of groups, some properties of groups and examples of groups. We shall also consider the definition of a subgroup and some properties of subgroups with examples. Before going to start the definition of group, we shall have some basic knowledge about the sets, particularly the sets of numbers. Here you can observe n is a set of natural numbers. As we all know that the set of all counting numbers 1, 2, 3 up to infinity, that set is called a set of natural numbers. So it is a set of numbers. Similarly, we can have any set which may have the elements like the alphabets A, comma, B, comma, C, comma, . So in this way we can have the set of alphabets or set of any well-defined objects we can have. The collection of well-defined objects is called as a set, and we also know what is meant by set of whole numbers. It is very simple. If you add 0 to set of naturals, we get set of whole numbers. And when we consider the negative parts, that is up to here, it is from here to here, it is set of whole numbers. If we consider -1, -2, -3 and so on up to minus infinity, that forms the set of integers. And the numbers of the form p by q, that is the numbers which are like fractions, they are comparatively larger than the set of integers. In the set of integers, there is a direct jump from 0 to 1, 1 to 2, 2 to 3. There were no fractional numbers here. Here, this was entirely the blank portion in the set of integers. However, when we consider the numbers which are of the form p by q, that fills all such gaps almost. So that type of numbers are called as the set of rationals. Along with rationals, we can have another set of numbers, very important, set of irrational numbers. So what are irrational numbers? The numbers which have infinitely many decimal digits which are non-repeating. Say for example, the value of pi is 3.14158, something like that. So this you can observe. After the decimal point, the digits are going up to infinity and the digits are not repeating here. So non-repeating, non-recurring decimal digits, if they are present in the given number, that number is called as an irrational number. So even we can have the numbers which are like square root of 2, square root of 3, cube root of 2, cube root of 5, and so on. So all such numbers, they are having non-recurring, non-terminating decimal digits. So they come under the category of irrational numbers. So if we consider the union of rationals and irrationals, so that is going to form a new set of numbers, which is very huge set of rational numbers. So we have now got the idea of the set of numbers. Now let us move on to the binary operation. What is meant by the binary operation? You please see, binary operation is nothing but it is some operation like addition. It may be addition, it may be multiplication, it may be subtraction, it may be division, it may be addition modulo n may be anything, or multiplication modulo n, or it may be any other operation which is defined by the user. So the operation which connects any two elements, then that particular operation is called as the binary operation. That is called as binary operation. Let us begin with the set of natural numbers. On the set of natural numbers, let us have this binary operation of addition. So you can observe here, if you take the sum of, that is the addition of 192. So 192 are operated with the binary operation addition. So 1 addition 2, answer you know very well, 3. And here you consider 4 addition 5, answer is 9. So you can observe the elements which we obtain as the result of the binary operation operated on any two elements of the given set. If that result again belongs to the given set, that is like n, then we say that the set is closed under the binary operation which is defined. So in this case we say that since for any two natural numbers, a comma b, we observe that a plus b is also the sum of two natural numbers is again a natural number. So therefore we say that set of natural number is closed under addition. So we say that the set is closed under that given binary operation. And we also say that the binary, that closure law is satisfied by this n. We say like closure law, if this property is satisfied, then we say that the closure law is satisfied. Similarly, you consider the binary operation of minus, same on the set of natural numbers. You take any two elements, for example 1 operated with minus on with the 2. So 1 and 2 are operated with minus. So 1 minus 2, answer is minus 1. You take any other two elements, 2 minus 4, answer is minus 2. 3 minus 3, answer is 0. You can now observe the results of these binary operations. They are not belonging to the original set. Therefore, we say that the binary, the set of natural numbers is not closed under the binary operation of subtraction. Similarly, we can have any binary operation. In general, we take the binary operation as star. We shall see it in the next slides. So next, you please observe another important property with respect to the same binary operation on the set, not necessarily set of natural numbers, we can say set of integers. So here we are considering the set of integers as the given set. Now you take the elements like 2, 3, 4. You see here 2 plus bracket 3 plus 4 is equal to bracket 2 plus 3 plus 4. So the answer in both the two cases is same. Therefore, here you can interchange the bracket. The bracket which was taken on the last two elements, that can be interchanged to the first and second element. So if this type of property is satisfied, if this type of axiom is satisfied, we call this as the associative property is valid. We say that the associative property is valid in the set of natural numbers, set of integers with respect to the binary operation of addition. Again, you please observe any integer added with 0 is giving you the answer the same integer. That is 2 plus 0 is equal to 2, or 0 plus 2 is also equal to 2. In general, for any a plus 0 is equal to a, and it is equal to 0 plus a. So this type of element if exists, see, this is the element which is playing a most important role. So if it is added to any element, that element is not losing its identity, the element is remaining same. Therefore, such an element is called as the identity element. We call such an element as the identity element. So in set of integers, we have the identity element existing, that is 0 with respect to addition. If you take multiplication, it is obviously 1. That is, any number into 1 is the same number. Therefore, 1 will be treated as multiplicative identity element in the set of integers. Now, if you look at this particular operation, binary operation, here 2 is operated with minus 2 with respect to the binary operation addition. 2 plus bracket minus 2. So minus 2 is another element, 2 is the given element. So 2 is added with minus 2, the result is 0. The result is 0. And even you can say that minus 2 plus 2 is also equal to 0. In general, for any element A, belonging to the set of integers, you can observe this particular property. You can observe this particular property, A plus of minus A equal to minus A plus A equal to 0. So for every A belonging to Z, there exists an element minus A again in the set of integers, So if such element is existing, we say that the inverse element is existing. So this minus A is called as inverse of A. It is denoted as A to the power minus 1. So read it as inverse of A, inverse of this A with respect to the binary operation addition. So if inverse exists for every element of the given set Z, then we say that the inverse law is valid. So we have seen what is meant by a set, what is meant by the binary operation, and what are the important properties that are being satisfied by the binary operation with respect to the given set, that is either set of natural numbers or set of integers. Now let us move on to the most important thing, which is the definition of a group. So what is the definition? You please see here. In the previous slides, we have taken particularly the set of natural numbers or the set of integers. They were particular. Now in order to define the group, let us have a general set G. So G can be either set of natural numbers or set of integers or set of rationals or set of reals or whatever it may be. So G is some general set of elements. So it is a non-empty set. So non-empty set is nothing but it should contain at least one element. It should contain at least one element. Then we say that the set as the non-empty set. Now with on the set of elements G, which we have already shown here, if there is defined a binary operation star, which satisfies these important properties. What are the properties? The first one is closure law. Axiom is also called as law. So closure property or closure law. What it tells already we have seen. If you consider any two elements of the set G, their binary combination, that is A star B, the binary combination under the binary operation addition, should also be an element of the given set G. If it is so, then we say that the closure axiom is satisfied. So the first condition is that the group G together with a binary operation star is said to be a group. If it satisfies the following axioms. First one is closure axiom. I have explained it. Second one is associativity must be satisfied. You can observe the bracket can be interchanged. That should also be allowed. So A star bracket B star C must be equal to A star B star C. So associativity should also be valid in G for any elements of G. So associative law should also be valid. The third important property is there must exist an identity element with respect to the binary operation star. So that element is denoted by E. So there exists an element E in the set G such that A star E equal to E star A equal to the same element A. That is, if you operate E with any element, you should get that same element back. So such an element E such an element E is called the identity element of group G, sorry, of G with respect to the given binary operation star. Here star is the general binary operation. It can be anything. Now, for every element A belonging to G, if there exists an element like A to the power minus 1, read it as A inverse, such that A star A to the power of minus 1, A to the power of minus 1 into A, you should get the element E back. So what is this element E? It is the identity element which we have already discovered, which we have already identified, which we have already noted in the above axiom. So that identity element should be recovered here by operating any element with this type of element. So this type of element should exist for every given element A. If that type of element exists, if this type of element exists for every A, then we say that this element as the inverse element of A under the given binary operation star. So if this property is satisfied, then we say that the inverse law is satisfied. So we say that the inverse law is satisfied. If all these four axioms are satisfied, then we say G as a group. We say this set G. Initially it was a set. Now it is becoming a group. With respect to the binary operation addition, sorry, with respect to the binary operation star, which is defined here. So now this combination, this ordered pair G comma star, we read this as a group G comma star, and this is a very basic fundamental algebraic structure which we have considered today in our journey of modern algebra. So it is a very fundamental algebraic structure. Group is a very fundamental algebraic structure. So what is the algebraic structure? Group, a set, non-empty set together with a binary operation defined on it, which satisfy some important axioms. So that is called as an algebraic structure, and this particular algebraic structure is now a group because it satisfies all these four axioms. Now, in addition to above four axioms, if another axiom which is again very trivial, that is, if you consider A star B, the answer should be same as B star A. A star B equal to B star A. If it satisfies, then we say that the commutative property is satisfied, or commutative law is satisfied. If the commutative law is satisfied by the set G along with the above four laws, so totally now 4 plus 1, 5 laws are satisfied by this G with respect to the binary operation of star. So this algebraic structure, now it is called as an abelian group. It is called as an abelian group. Now, what are the finite and infinite groups? You see, very simple definition we have. As we have studied a finite set and an infinite set. A finite set is one in which the number of elements is finite. Infinite set is one in which the number of elements is infinite. Similar to that, the group is said to be a finite group if G contains finite number of elements. We bother about only the set G, not about the binary operation star. We do not have anything to do with this star while defining the finite group. The number of elements in G, if it is finite, or in other words, if G is a finite set, then this group we have already defined it, is called as a finite group. Otherwise, it is called as an infinite group. Now, another very important concept. See, in the set of in the set we have defined the number of elements. If the set is finite set, and if the number of elements, if A is a given set, the number of elements in that set is called as the cardinality of that set. We have denoted it by the A enclosed within two vertical bars. So we called this as the cardinality of a set. That is the number of elements in the set. Similarly, the number of elements in the group, particularly the finite group, is called as the order of that, and it is denoted by the symbol O of G. So O of G is order of the group. Finite group will have a finite order, whereas infinite group will be of infinite order. Yes, I hope it is clear to you. Now we have another important sign convention, that is, for the sake of simplicity, instead of denoting the binary combination A star B, we can simply use the notation AB. So AB is nothing but again A star B. That you have to take into your mind. So A star B is not necessary to indicate explicitly every time. So for the sake of brevity, we can simply show it as AB. AB stands for A operated with B under the binary operation star. So that should be understood. Next, we shall have some simple properties of a group. So in the group, I have already shown you, we have already seen that the identity element must exist in a group. Identity element must exist in a group, because to become a group, it should satisfy the identity law. Therefore, identity element must exist in a group. Whenever the identity element exists, it is unique. See, the group cannot have more than one identity element. Always the identity element in the group is denoted by E, which is always unique. And inverse property we have seen, for every element of the group, the inverse exists, and inverse of every element is unique. That is, for example, you have the set of natural numbers. If 2 is the given number, its inverse under addition is, sorry, you don't consider set of natural numbers because we don't have -2 there. You consider the set of integers. In the set of integers, if you consider 2, its additive inverse is -2. And this -2 is the unique element with respect to 2. So, in general, for any element A, the inverse is unique. So, the inverse of A is always unique. That is the second important property. And this is the third important property. Inverse of A is again A. Just you can observe here. Minus of 2 is obviously 2. Therefore, in general, not necessarily with additive binary operation, with respect to any general binary operation star, you can have A inverse as the inverse of the element A. Inverse of A is the element A back. And if you consider AB here is nothing but A star B. A operated with B, A binary operation B. So A star B whole inverse is equal to, you see, B inverse star A inverse. That means the elements are reversed here, and therefore it is called as reversal law of inverses. Very, very important. You should always remember it. So it is inversal law of inverses. Reversal law of inverses. And this is one more very, very simple thing. Inverse of identity element is the identity element itself. You consider 0, its identity element is 0 itself. There is no meaning to write -0 or +0. Identity element, if it is 0 under addition, its inverse is 0 itself. So like that, not necessarily with respect to additive identity 0, with respect to any identity element E, the inverse of that is E inverse is the element itself. The identity element is the inverse of itself, we can say like that. And now we have this very simple and which we have already used in our earlier analysis. Now let us recall it. You have A star X, AX equal to AY. If you have this is equal to this, you can simply cancel this X. So therefore, this law is and after cancellation, you will have x is equal to y. And this property is called as left cancellation. Why it is left? Because we are cancelling the element to the left. If you cancel the element to the right here, then you will get x equal to y, and this law is called as right cancellation law. Now, we shall have some simple examples of groups. See, I have already shown you set of integers forms the group with respect to binary operation addition. Set of, you can observe all the four properties 1, 2, 3, 4. First one was closure, second one identity, first one closure, second one associativity, third one identity law, fourth one inverse law. All these four laws will be satisfied by the set of integers with respect to the binary operation of addition. Therefore, this is a group. Very trivially we can say. Now, the set of rationals again satisfies all the four axioms of the group. Therefore, with respect to the binary operation of addition, therefore, this also we call as the group under the binary operation addition. Now, set of real numbers is also a group. Set of complex numbers is also a group. And in all these cases, the sets we considered are the infinite sets. Set of rationals, set of integers, set of real, set of complexes, all are infinite sets. Therefore, the groups are infinite groups, and they are abelian groups in addition because they satisfy this property, that is AB is equal to BA. You should understand that A star B, this is A star B equal to B star A. So this property is also satisfied in each of these examples. So therefore, these are called as abelian groups, and since they have infinite number of elements, infinite abelian groups we call them as. Now, you please observe the example here. Set of natural numbers is not forming a group. Set of is not a group, because the reason is very, very straightforward. Because the identity law fails, because the identity element with respect to addition is 0. In n, 0 is not there. Therefore, the identity element when it is absent, we say that n is not a group with respect to addition. However, it can satisfy two axioms. The two axioms are the closure axiom, which I have already shown you in the beginning. N satisfied the closure axiom, and n also satisfies the interchange of brackets, that is associativity axiom. So first and second axiom, if they are satisfied, then we call it as a semigroup. So semigroup is another definition which we have to consider. G with a binary operation star is said to be semigroup if the first one closure law is satisfied and the second one associative law is satisfied. If only these two laws are satisfied, so the closure law and associative law, if they are satisfied, we call this as the semigroup. Now, however, n is a semigroup with respect to addition, but it is not a group. Now, with respect to multiplication also, it is not a group. However, it has a multiplicative identity element 1. It has a multiplicative identity element 1, but every element of set of natural numbers do not possess the inverse under multiplication. For example, you have the element 2 belonging to the set of natural numbers. Its inverse is something like 1 by 2, because when you multiply 1 and 2, answer should be the identity element 1. We have said that the identity element is 1 with respect to multiplication. So with 2 you have to multiply 1 by 2 so as to get the identity element 1 back. But we observe that this 1 by 2 is not present in the set of natural numbers. Therefore, it is not forming a group with respect to multiplication. The set of natural numbers is not forming a group with respect to multiplication. However, it is a semi-group, and even the identity law is satisfied. Therefore, we say it as semi-group with the identity element. Similarly, set of integers with respect to multiplication is not a group, because inverse element, just like 1 by 2, the element of the type 1 by 2 is not present in the set of integers. Therefore, we say that set of integers is again not a group, with respect to the binary operation of multiplication. However, you please observe the singleton set 1, the set containing element 1. You can have a singleton set also. It forms a group, particularly a finite group, because this set, in place of G, we are having a singleton set that is denoted by this. It is forming a group with respect to binary operation of addition, because it satisfies all the properties, because there is no need of checking the 1 star 1. 1 star 1 is 1, and 1 star bracket 1 star 1 is star, here is multiplication. 1 into bracket 1 into 1 is bracket 1 into 1 into 1. That is associative law is satisfied. 1 itself is the identity element. Identity law is satisfied. And identity element is inverse of itself. Therefore, 1 is inverse of 1 itself. Therefore, all the 4 axioms are satisfied. Therefore, it is the group. And it is satisfying one more property. That is 1 into 1 is equal to 1 into 1. That is AB equal to BA. That type of property is also satisfied. Therefore, it is now an abelian group, particularly the finite abelian group. And this is also forming the finite abelian group. And this 1 omega omega square is again a finite abelian group. And 1 minus 1 I minus I, the element, the set containing 4 elements, is again a finite group. So we have considered this. See, these 2 elements are the square roots of 1. These 3 elements are the cube roots of 1. Cube roots of 1 are 1 omega omega square, and these elements are the 4th roots of 1. So we say that the set of square roots of 1, cube roots of 1, 4th roots of 1 are all forming the group with respect to the binary operation of multiplication. So these are the examples of groups. Now let us define another very important concept, that is subgroup. Just immediately after defining a set, we usually define a subset. So what is the subset? See, if A is a given set, and if B wants to be the subset of A, B wants to be the subset of A, every element of B must be an element of A. That is, every element of B must be an element of A. Then we say that B is a subset of A. Similarly, to a group, with a group, we can define the subgroup. So here G is a given group with respect to binary operation star. Now H is any non-empty subset. See, it should be non-empty subset. It should contain at least one element. So non-empty subset of G. Then H is called subgroup of G if H is a group in itself under the same binary operation star. So H comma star, this should be a group by itself. It should satisfy all the 4 properties which we have already defined for the group. This H should satisfy all these 4 axioms with respect to the same binary operation star. Then we call this H, which was the subset of G, as the subgroup of G. Not only the subset, this subset will become a subgroup now, subgroup of the original group G. And now we know that every set, you consider the set G, every set is a subset of itself. Every set is a subset of itself, and that is particularly an improper subset, we call it as. Okay, and therefore, if G is a group, originally G is a group, and we know that G is a subset of G, therefore this G is also called as the subgroup of itself. So that type of subgroup is called as a trivial subgroup. Or improper subgroup. we have one more trivial subgroup, the singleton set containing the identity element. See, to become a subset, it should contain the identity element, and identity element is always unique. So whatever is the identity element in G, that should also be in H. Therefore, identity element will be present in each of the subgroups of a given group. Whatever is the identity element of a group G, that will be present in each of the subgroups. It is not necessary that group should have only one subgroup. There may be more than one subgroups, H, K, or H1, H2, H3, like that. So in each of the subgroups, that identity element should be present. Then only that becomes a group, and then that becomes a subgroup. Now, here the singleton set E will become a, first of all, it will become a subset of G. And I have shown you in the previous slide that singleton 1 is a group with respect to multiplication. Similarly, this singleton set containing element E is a group with respect to the binary operation star. So this group now, this set is becoming a group, and therefore this is called as the subgroup of G, and particularly again the trivial subgroup or improper subgroup of the given group. So for every group G and the singleton, the set E, are the two trivial or improper subgroups that we have to keep in our mind. Now, let us consider proper subgroup. So proper subgroup is any other subgroup. So any subgroup other than the trivial subgroup, that is called as a proper subgroup. For example, you consider group C, that is set of complex numbers with binary operation addition. This is a set. This is a group we have already shown in the example section. Now, the set of reals together with G, this is a group. So this is forming a subgroup of this group, because we know that set of reals is subset of set of complexes. So set of reals is subset of set of complex numbers. Therefore, this group is a subgroup of this group, and this group is a proper subgroup. And here, this group, the set of integers together with binary operation addition, is a subgroup of group of real numbers with binary operation addition. The set of naturals is not a subgroup, because we have seen that this is not at all a group. Therefore, it is not becoming a subgroup. Whereas this the set containing two elements, -1, 1, together with the binary operation of multiplication, is a group we have already seen. This is the set of elements of square root of 1, and this is fourth root of 1. This set is containing the elements which are fourth roots of 1. So this is a group, and it is a subset of this. Therefore, this group is a subgroup of this group. So like this, we have defined the subgroup. Now let us consider an important theorem. So in this theorem, see, this theorem is going to become a necessary and sufficient condition for the subgroup. So what it is, necessary and sufficient condition means if and only if type of statement we have to prove. So what is if and only if? That means we have to prove bidirectional, biconditional statement. That is, if this part is true, then we have to show that this part is true. Conversely, if this part is true, we have to show that this part is true. That is, what is the statement? A non-empty set H, actually it should be the subset. I should have written here subset. A non-empty subset H of a group G. G is a group with respect to a binary operation star. If it is not mentioned, it should be understood. Is a subgroup. It is a subgroup of G, what H is a subgroup of G if and only if for any two elements AB belonging to H, AB inverse A star B inverse, it is not AB whole inverse, it is A star B inverse belong to H. So this type of closure property, if it is satisfied, then we say that H is a subgroup. So you please understand the statement. If H is a subgroup, this must be valid. If this is valid, H must be a subgroup. So that we have to prove like this. First, suppose that. See, we shall always consider the statement first suppose that. Whenever we have if and only if type of result to be proved, we consider in the beginning first suppose that H is a subgroup. We first assume that H is a subgroup of G. Where H is a subgroup of G, H must be a group under the same binary operation as that we have defined for G. So when H is a group, for any element B, say belonging to H, inverse of B must exist. That is the existence of inverse that we have already seen. So inverse of B must exist. Now we have two elements. One is A for any element A, and for any other element B inverse. We are not considering B. We are considering this B inverse which has already existed in H as per our inverse law. So we are having two elements which are belonging to H. Then their combination is also in H. That is according to the closure law. According to the closure law, A star B inverse, that is AB inverse, is also in H. So what we have proved, for any two elements A and B belonging to H, at the end we have proved here this thing, AB inverse belonging to H. That is what we were asked to prove. So the first part we have completed. That is the direct part we have proved. Now go for the converse part. So what is the thing? We have to assume conversely. Now conversely, suppose that for any two elements AB belonging to H, AB inverse belong to H. Now our job is to prove that H is a subgroup. To prove that H is a subgroup, we will prove that H is a group. So to prove H is a group, let us consider an element A. For element A belonging to H, A inverse also belongs to H. We have to write A inverse. A inverse belongs to so why it is A inverse? Just a minute. It is not A inverse because we have to prove that A inverse exists. So for A belonging to H, again I have written A belonging to H because I want to have this type of expression. A here, and this A is playing the role of B. So for A and A belonging to H, A inverse belongs to H as per this equation number 1. As per this equation number 1, A inverse belongs to H. So this is by 1 with B replaced by A in 1. Now what is A into A inverse? This is E. Why A into A inverse is E? Because we have seen this in G. When A into A inverse is E in G, that should also be E in H. And when A into A inverse belongs to H, the answer of this, that is E, should also be in H. So we have proved that the identity element exists in H. Now for E belonging to H and A belonging to H, we have A B inverse just like this, A B inverse just like that, E A inverse. E is A is B, but in equation number 1. So E A inverse is belonging to H. So what is the product of any element with E? It is the same element A inverse. So what we have proved, for any element A, there is an existence of its inverse. So therefore we say that every element of H has the inverse element. Now the other two properties are very much straightforward. Closure axiom is valid in the superset G, therefore it should also be valid in the subset H. Associativity law is valid in G, the superset of H, therefore it is also valid in H. When these two axioms are valid in the supersets, they must be valid in the subsets, therefore they are valid in H. So H is now satisfying closure axiom, associativity law, inverse law, and identity law. So therefore all the four laws are satisfied, therefore H is becoming a group. When H is a group and H is a subset, H is a subgroup. H is a subgroup of G. So we have proved the theorem. That is, when the condition AB, for all AB belonging to H, AB inverse belongs to H, then H is a subgroup. And conversely, when H is a subgroup, this particular condition is satisfied. So this completes the proof of the theorem. Now we have another theorem, which is the refined, which is the simplified version of the previous theorem, not different. So what is that? If H is any non-empty subset of the group G, H is a subgroup. Again, if and only if. So again, it is necessary and sufficient condition that these two conditions are satisfied. What are those two conditions? For all AB belonging to H, their combination, that is A star B, AB should also belong to H. And for A belonging to H, its inverse should be belonging to H. So if these two conditions are satisfied, then we say that H is a subgroup, or conversely, when H is a subgroup, these two conditions will be satisfied. So this theorem is exactly similar to the previous theorem. Therefore, I don't want to prove it. I ask you to prove this by yourself. Therefore, this is an assignment to you. Please try to prove this theorem. Okay. Next, consider the third theorem. Very, very important. Intersection of two subgroups is a subgroup. Let us consider H1 and H2 as two subgroups of G. Now, since H1 is what we have to prove? We have to prove that the intersection of H1 and H2, that is H1 intersection H2, is a subgroup we have to prove. So, we have considered two subgroups, H1 and H2, and we are now using the definition of subgroup of H1. Since H1 is a subgroup, it should satisfy the condition. So what is the condition? For all A belonging to H1, B belonging to H1, AB inverse must be in H1. Again, since H2 is a subgroup, for all A belonging to H2, for all B belonging to H2, AB inverse belong to H2. This is as per theorem number 1. So what we have, you please observe, what we have, for all A belonging to H1 and A belonging to H2, we see that when A is in H1 and in H2, and is very, very important here. When A is in H1 and H2, we say that A is in the intersection of H1 and H2. Similarly, when B is in H1 and B is in H2, B is in the intersection of H1 and H2. Now what we have, two elements A and B are belonging to H1 and H2. Now also we observe that from equations 1 and 2, you please observe equations 1 and 2. AB inverse is in H1 and AB inverse is in H2. As a result of that, AB inverse, see, that is what we are writing. AB inverse is in H1, AB inverse is in H2, therefore AB inverse is in H1 intersection H2. So what we have proved, that is, if A comma B are any two elements of H1 intersection H2, AB inverse is in H1 intersection H2. So this is we have proved here. So it is in H1 intersection H2. So therefore, what can we say now? We say that H1 intersection H2 is a subgroup of G according to theorem number 1. So however, we have to take into account that union of two subgroups need not be a subgroup. This is another theorem. Here, if H is a subgroup, then inverse of H is H. So what is inverse of H? So inverse of H is the set containing all the elements which are the inverses of the elements of H. So that we have to prove that H inverse is same as H. Since H is a subgroup, for every element A belonging to H, inverse of that element belongs to H. So when A inverse belongs to H, it means inverse of inverse of this element, that is inverse of this, should also be, this should present in H inverse. So here for every element A belonging to H, inverse of inverse is A. So inverse of A is A. A is belonging to H inverse. So what is there? H, for all A belonging to H, we have proved that A belonging to H inverse also. Therefore, every element of H is an element of H inverse. Therefore, H is subset of H inverse. Similarly, now since H is a subgroup, it must contain inverse of each of its elements. Therefore, H inverse, that is containing the inverse elements of H, and inverse elements of H are also present in H. Therefore, every element of H inverse is also an element of H. Therefore, we have H inverse is subset of H. When these two are true, that is, when in order to show that any set is equal to another set B, we have to show in set theory that A is contained in B and B is contained in A. If we prove this thing, we say that A is equal to B. Therefore, H inverse is equal to H. So this completes the theorem. Now we have another important theorem. For any two subsets HK, H and K are the two subsets of a group G. HK, see the product of H and K is a subgroup of G if and only if HK is equal to KH. This is an important theorem and this is quite lengthy theorem. Already we have proceeded for a more than 30 minutes. Therefore, at this point of time, I want to stop to this session. So this proof we will consider in the next class. So I thank all of you for watching this video, and in order to prepare the this content, I have used my own book which I have written for BSc BSc third semester mathematics syllabus as per SCP. So please try to refer this textbook, and once again I thank all of you for watching this video. Thank you once again.